the distance problem. Now let's consider the distance problem. Find the distance traveled by an object during a certain time period if the velocity of the object is known at all times. In a sense, this is the inverse problem of the velocity problem that we discussed in section 2.1. If the velocity remains constant, then the distance problem is easy to solve by means of the formula distance, which is equal to velocity times time. But if the velocity varies, it's not so easy to find the distance traveled. So we investigate the problem in the following example. Example 4, estimating a distance. Suppose the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval. We take speedometer readings every 5 seconds and then record them in the following table. So here's the time in seconds, 0, 5, 10, 15, 20, 25, and 30. And the velocity is in miles per hour. We have 17, 21, 24, 29, 32, and 31, and 28. So the first thing we want to do is we want to be able to convert this to feet per seconds. So in order to convert, we're going to convert this to feet per seconds. And so what we want is we want this to be the velocity to be in feet per second. So therefore, we would get 25, 31, 35, 43, 47, 46, and then 41. So now the first thing we want to do is we want to be able to assume that the velocity is approximately constant during the first 5 seconds and the initial velocity at t is equal to 0 to estimate the distance traveled from t is equal to 0 to t is equal to 5. Okay, so in order to do that, what we're going to do is we're going to take 25 feet per second times 5 seconds. And so that gives us 125 feet. Okay, now next what we want to do is we want to be able to assume that the velocity is approximately constant during the next 5 seconds and the initial velocity at t is equal to 5 to estimate the distance traveled. So from t is equal to 5 to t is equal to 10. So we can take now 31 feet per second times, that's 5 seconds, which is equal to 155 feet. And so now what we want to do is we want to be able to add the distance estimates for each subinterval to estimate the total distance traveled. So what we're going to do is we're going to go from t is equal to 0 to t is equal to 30 because it goes from 0 to 30. So what we're going to do is we're going to take that 25 times 5 plus 31 times 5 plus 35 times 5 plus 43 times 5 plus 47 times 5 plus 46 times 5. And so that gives us approximately 1,135 feet. Okay? So, again, these are the subintervals going from 0 to 30. All right, now, what happens if we look at the left endpoints and then we look at the right endpoints? Well, let's take a look at the graph here. So if we wanted to find L6 using the left endpoints, we basically do the same thing here. That means we're going to use the left endpoint. So we're starting with 25, 31, 35, all the way to 46. So we would get the same result. We would get 25 times 5 plus 31 times 5 plus 35 times 5 plus 43 times 5 plus 47 times 5 plus 46 times 5. And that gives us 1,135 feet. Okay, so now what if we took the other graph here, okay, and let's say that we started now with the right endpoints. So if we wanted to find the right endpoints, then what number do we start with? Well, we start with 31, 35, 43, all the way to 41. So if we take 31 times 5 plus 35 times 5 plus 43 times 5 plus 47 times 5 plus 46 times 5 plus 41 times 5, then we get the result of 1,215 feet.